Okay, so this is second part of chapter 3 on exponential and logarithmic functions here. So here we're just going to look at what does the logarithm actually mean, how to evaluate logarithms, how to use the change of base formula in your calculator to evaluate a logarithm, and then how to expand and condense logarithms when they've got variables in them. So most of what you'll be doing for your homework is going to be the expanding and condensing, but there will be some evaluating as well. So we know that if you log both sides of an equation, it allows you to bring down the power. Okay, so you learned that last year. What we're going to be looking at mostly is what happens when someone gives you a logarithm. Okay. And what happens is that you take the base and you put it underneath whatever it's equal to. Okay, so we imagine that's like we're having a chicken fight here. The b comes up and lifts up the y on its shoulders. So for this first problem here, we want to write equals y. Okay, so the 3 comes up underneath the y, leaving us with 3 to the y equals whatever was on the inside, and that is 81. Okay, and what I need to do now is I need to say, can I think of some power that 3 could be raised to that would give us 81? Okay, so you can look in your calculator, do like 3 squared is 9, 3 to the 3rd power is 27, 3 to the 4th power is 81. Okay, that's the guy I wanted. All right, so you got to kind of guess, and then you say, okay, y was equal to 4. So that means that log base 3 of 81 is equal to 4. Okay, so then this next guy, here we'll say equals y. 5 comes underneath, so we'll say 5 to the y is equal to the square root of 5. Okay, so square root is a 1/2 power. 5 to the 1/2. Oh, okay, now the bases match. So y is equal to 1/2. So the logarithm then is 1/2. Okay, so this next one, I'm going to do this one in 2 steps here. I'm going to say that equals y. All right, bring the 7 underneath it. 7 to the y is equal to 1 over 49. Okay, that's a reciprocal. So I'm going to say that that's really 49 to the negative 1. Okay, because it was 1 over, so 49 to the negative 1. And then I'm going to say, well, 49 is 7 to what power? Okay, so 7 squared, and then to the negative 1. Now there's a rule that says that if you've got something to a power and you raise it then to another power, that you end up multiplying those 2 powers together. So that gives me 7 to the negative 2. Okay, so I had 7 to the y equals 7 to the negative 2. That means that my logarithm, log base 7 of 1 over 49, was equal to negative 2. All right, now this one here, log base 2 of 2, okay, that's essentially saying 2 to the y equals 2 to the what power? Well, 2 is 1, or 2 is to the 1st power here. So y equals 1. Any log of its own base is equal to 1. Okay, so that one wasn't terribly exciting here. Let me make it a little different, though. Let me say that I want log base 4 of 8. Okay, so log base 4 of 8. That means that 4 to the y is equal to 8. Okay, well, you won't find any easy-to-guess power that you could raise 4 to in order to get 8. In fact, if you raise 4 to the 2, 4 squared is 16. Okay, that's too big. So what I'm going to do instead is I'm going to say that 8 is really 2 to the 3rd power. Okay, 8 is 2 to the 3rd power. And I'm going to see if I can turn 4 into 2 to some power. Okay, so 2 squared to the y, which we can rewrite as 2 to the 2y, is equal to 2 to the 3rd. Okay, 2y equals 3, so y equals 1.5. Okay, so coming over here, log base 4 of 8 is 1.5, and you can check in your calculators that 4 to the 1.5 power is equal to 8. Check that right now. Okay, we will prove this formula later when we start solving equations, but for right now it's enough to just remember it. Okay, if you want to do log of a base, or log base something of some argument, okay, you can do log of the argument over log of the base. Okay, and in this case, log of x is really log base 10 of x, and that's on your calculator. Your calculator has an log for log base 10. It also works if you do the natural log. Okay, so the natural log of x is really the log base e of x, and your calculator has that as well. Either one of these will work as long as the logarithm on top is the same base as the logarithm on the bottom. So if you had a calculator that for some reason really wanted to do log base 2, say it's binary or something, you could do log base 2 of x over log base 2 of b, and you'll get the same answer that you would have gotten with the natural log or with the common log base 10. So let's just try this here. We'll do the natural log of 512 over the natural log of 8 and see what we get. Okay, so whether you use natural log or common log, you should get 3. Okay, and that kind of makes sense because we could say that 8 to the 3 is 512. Okay, that's essentially what this was asking. It was saying, what power could we raise 8 to get 512? We could raise it to the third power. Okay, so this next one here, natural log of 4 to the 3.2 all over the natural log of 4. Alrighty. Now what's going to happen there is, well, you can type it straight in. Okay, and if you do it with parentheses, it should give you 3.2. All right. Well, we know actually that 3.2, that power, can come down to the front. We've seen that before from Algebra 2. We did that a lot. Okay, bring down the 3.4. Well, that gives you 3.2 natural log of 4 over natural log of 4. Okay, well, that should be equal to 1. Okay, so it makes sense that if you've got something with a power and the base was the same, that it really should just cancel out and give you that power. Okay, this next one we'll say the natural log of 1 over 32 over the natural log of 2. Okay, and the calculator says that's a negative 5. Okay, and we can check that by saying 2 to the negative 5. All right, well, that's 2 to the 5 is 32, but it's negative, so 1 over 32. Now this last one is similar to the one that I made up on the previous page here. If you say natural log of the square root of 2 over the natural log of 16, okay, the calculator will tell you that that is 1/8. All right, let's see if we can also do that going the other way, just for more practice here. Okay, so we're going to say that 16 to the y was equal to the square root of 2, and square root of 2 is 2 to the 1/2. Okay, well, you're not going to guess any power of 16 that gives you 2, but you could turn 16 into some power of 2, and it's 2 to the 4th. So 2 to the 4th to the y is equal to 2 to the 1/2. 4y is equal to 1/2, so y is equal to 1/8. Okay, so that gives you the same answer as if you use the change of base formula. So anytime we just have plain old numbers on the test, you'll be able to just use the change of base formula, but we need to know how to convert these into exponential form and solve, because sometimes we'll have variables, and in that case the calculator is not going to help you. Okay, so just a quick review of what you already know about exponents from Algebra 2. One is that if you multiply two bases together, then you're going to add their exponents together. So let's think about this base being raised to a power as a function that has an inside and an outside. Okay, we've got two functions multiplied together. Multiplication occurs on the outside. So multiplication outside the function produces a single function with addition inside. Okay, the function being base raised to a power. Take two of those, multiply them together, you get a single base raised to the sum of their two powers. Okay, well, division, put something in the denominator. Okay, well, that thing in the denominator could actually be have a negative power. So b to the x times b to the negative y. Okay, well, that means just then add the powers together. Right, that negative y that is getting added on here. Okay, so that's proof of why it works, given that the product property works. We can summarize it as division on the outside is equal to subtraction on the inside. Okay. And then we've already seen this one, that if you have something raised to a power and then raised to another power, that you end up getting them multiplied together. So multiplication, or I'm sorry, exponentiation, exponents on the outside gives us multiplication on the inside. Now, don't fall into the trap of just saying, okay, multiplication is addition and division is subtraction and exponentiation is multiplication. Don't do that. Okay, we need to distinguish between the multiplication on the outside in the first rule and the multiplication on the inside in the last rule here, because when we go to turn these things backwards, the inside and the outside are going to get swapped. Okay, it's because so when you invert a function, you swap its x's and y's, and it's the x is what goes in and the y is what comes out. So if you swap the what goes in and what comes out, you're going to swap the outside and the inside. So you swap that around, okay, and it ends up giving us multiplication on the inside of a logarithm is equal to addition on the outside. Okay? Similarly, division on the inside is equal to subtraction on the outside. And a power, an exponentiation on the inside is equal to multiplication on the outside. Okay, so we had to keep straight what was the inside and what was the outside. Okay, and that way when we reverse it, we don't get mixed up. Okay, so first thing we're going to do is we're going to try to expand. Okay, and when we expand here, we want to get rid of all of our powers. Okay, we should have no powers or roots left over once we've done the expansion. Okay, now when you expand, you're going to do your order of operations, PEMDAS. You're going to do it backwards, like when you solve for x. If you're trying to isolate x, okay, you've got to actually take care of your addition first. Move the addition to the other side with subtraction, and then you got to move your multiplication to the other side with division before you can undo your powers by taking some sort of root. So no addition occurs. In fact, we don't even have a rule for doing addition inside a logarithm. So we'll start with multiplication. Okay, start with multiplication, and we will we'll split it up. Log of 12 plus log of x to the 5th plus log of y to the negative 2. Okay, so once we've split up all the factors, all the things being multiplied together, then we can bring the powers down. Okay, so log of 12 just stays the same. That's just a number. Plus, bring down the 5. 5 log of x, and then bring down the minus 2. Minus 2 log of y. Okay, so now for this next one here, We've got division. So I'm going to say ln of x squared minus ln of, and this square root is really the 1/2 power. So I'm going to go ahead and, since I have to write a separate step anyway, let me go ahead and just do my turning it into a 1/2 power right here. And then I'll bring out my powers. Okay, so 2 ln x minus 1/2 ln 4x plus 1. Now, it's important at this point that you stop. Stop, because there is no addition inside. There's no rule that lets you separate addition inside. So we're done. Okay. Once you get down to addition inside of a logarithm, don't go any further. Okay, so this next one here, it's going to be kind of a pain. I got to write out log 13 a bunch of times, so I'm going to try to do as few steps as possible. Okay, so log 13 of 6, that's a number. Plus, okay, it's going to be log 13 of 8 to the 3. That 3 power can come down. 3 log 13 of A plus log 13 of B plus 4 log 13 of C. Okay, so just to indicate, so that I don't have to write out another step, see that these powers that were up there came down. And I'm going to grab my lasso of truth and move that over. All right, so this last one here, we've got some divisions. There's really 2 divisions going on. Okay, every factor in the denominator is divided. So that means that they're all going to be turned into subtractions. So ln of 3y plus 2 minus ln of 4 minus ln of y, and that y had a 1/3 come down. Okay, so in general, as long as the thing that you started with, like here, was in its simplest form and didn't have any negative powers in strange places, okay, as long as this was in its simplest form, once you start doing subtractions for your denominator, it should all be subtractions. Okay, so now somebody could give you one to condense that has an addition at the end. We'll see one like that in a minute. Okay, but if this is in its simplest form, once you start subtracting, there shouldn't be any additions coming after it. Okay, so now let's see what happens when we condense these things. Okay, always put your powers up first. Okay, so when you're condensing, we're going to do PEMDAS in order, like as if we were evaluating. Okay, PEMDAS in order, like we're evaluating, and we want to go, okay, until we have one logarithm, and we don't want have any negative powers. Okay, so anything that would have had a negative power needs to actually just be in the denominator. All right, so this 4, he can come up here. This 1/3, he can come up here. All right, so log base 3 of x to the 4th minus log base 3 of x plus 6 to the 1/3. So deal with the powers first. Deal with exponents first there. Okay. And then we have to deal with the subtraction. So now I have a single logarithm, base 3. And then I have a fraction. X to the 4th is on the top, and then the 1/3 power is a cube root. So I'm going to write it that way. Okay, you could write it as x plus 6 to the 1/3 power on the bottom, but I want to show off the fact that I know that that's a cube root. Okay. Now, so it's okay if you have a 1/3 power on the bottom. I won't be mad. Don't have any negative powers on the bottom or on the top. And also, don't do a logarithm over another logarithm. Okay, if I have a log base 3 of something over another log base 3 of something, that's a change of base. We're not changing any bases here. Okay, these condensings should always be a single logarithm and it could have a fraction on the inside. So this one here, we'll pull up the 6 and we'll pull up the 3. ln of, okay, I'm going to put x to the 3 first, just because monomials traditionally go in front of binomials when you write these things. So, and then x minus 4 is to the 6th power. Okay, so then this one here, I'm going to pull that negative 5. He's going to come up to the top. I kind of made that a little close. So that whole negative 5 is going to come up to the top. All right, so I have log base 2 of x plus 1 to the negative 5 plus log base 2 of 6x, and that is to the 3. Okay, so then the trick here is that we do a single log base 2. And that x to the negative 5 is really x to the 5th in the denominator. So x plus 1, so actually x plus 1 to the negative 5, x plus 1 to the 5th in the denominator. Okay, and then the other one, I need that parentheses to stay on there. 6x cubed needs to keep its parentheses unless I want to raise 6 to the 3rd power as well and get 216. So 216x cubed is fine, 6x all cubed is fine, but 6x cubed, just 6 times x cubed, is not fine. The 6 also gets the 3rd power on it as well. Okay, so here I see one where the negatives all come at the end. Okay, which means that once I get into those negatives, everything is in the denominator. So I'll pull up that 4 right there. Everything else is good already. So I'm going to have 3x plus 5, and on the bottom I'm going to have x to the 4th, and I'm also going to have x minus 1. Okay, so both of those things are in the denominator. Both of those things are in the denominator. Okay, now someone could try to play a little trick on you and say instead that they wanted you to do this one. ln of 3x plus 5, okay, minus 4 ln of x plus ln of x minus 1. Okay, if that happens, the 3x plus 5 goes on the top, the x to the 4th goes on the bottom, but x minus 1 also goes in the top. Okay? So if there's addition at the end, even if you've already started writing things in the bottom, in the denominator, it still needs to go back up into the numerator. Okay, so don't say, okay, I did minus, minus ln x to the 4th. That puts x to the 4th in the bottom, and then times. Don't put your minus 1 down here in the bottom. No, okay. That plus here is the same as if it had been added right there. You're going to get the same thing. Okay, and just one little thing I want to say about the homework here. It starts off saying, "Hey, can you guys solve these things, algebraically, showing your work?" These are a whole lot easier if you apply your rules first, though. Okay, so if I wanted to say, okay, 5 to the y equals the 4th root of 25, that's kind of hard. Yuck. Okay. Instead, what I'll do is I'll take this, pull it down, and get 1/4 log base 5 of 25. Okay? And we'll call that 1/4 y. Okay? Now I can say 5 to the y equals 25. All right, equals 5 to the 2. 25 is 5 to the 2. Y equals 2. 1/4 times 2 equals what? That's a whole lot easier. Okay. Similarly, with these guys here, you can pull those 3's down. Okay. Multiply the 3 times the 9 and the 5 times the 4. Okay. ln of e and ln of e, your calculator can do for you. All right, and you're going to get something that simplifies really easily. Okay, so same thing here. This is really the 1/2 power. You can pull him out front, simplify with the 2, and then just do 3 to the y equals 27. Okay, everything after that is pretty self-explanatory.